Welcome to IPMWORKS e-learning modules. My name is Tito Caffi and I'm an associate professor in plant pathology from l'Università Cattolica del Sacro Cuore in Piacenza, Italy. This video is part of the Module 4 Integrated Disease Management, and it will present the chapter 4.3 Applied Epidemiology for Disease Control. In this module, we are discussing the type of resources of epidemiological models and decision support system we can use for improving disease management into an holistic approach and in order to apply IPM into our fields. Modeling for plant diseases is a very interesting tool and is the aim of epidemiological study. So we are trying to understand how a pathogen is dealing with its own target, with the proper host in a certain environment, because we would like to simulate the behavior of the pathogen, because in such a way we can understand when and how big a risk of infection is present. In this way, we can understand and better apply disease protection strategy. A model represents a simplified simulation of reality, where reality is, for us, the pathosystem. So a certain pathogen on a specific host in a certain environment. Modeling should be based on a deep knowledge of this reality, because we have to keep in mind that a model is a simplified simulation. So if our knowledge of the reality is not strong and robust, of course, you can easily understand that the simplification of an uncertain knowledge will be a disaster. But if we can work on a deep knowledge of reality, we can develop models that can help us in increasing the efficacy and the quickness of the decision-making process, so we can be much more precise and timely in application of plant protection products, or generally speaking, the application of action, mitigation action to control diseases. They can also help us in understanding the epidemic processes and to elaborate better or enhanced disease protection strategies. So we have to focus on the disease triangle, the pathogen, the host, and the environment. And we have to keep an eye open on that trigger, the time that is pushing the epidemic to spread over time and space. That means from the starting point of a disease in our field to spread over the other plants in our field. Of course, we have many different types of modeling approach. Generally speaking, we can categorize two major approaches. One is the empirical modeling approach. That is so-called the data-based approach, that is used to create models who can describe the observed system in a mathematical way. I'm not sure if we can say from the other side, but a different approach is the mechanistic one. We are calling those models also process-based model, and they are used to describe the system based on what we know about the system and how the system is working in relation to some influencing variable. which is the main influencing variable, is the weather. So we can think about rainfall, temperature, relative humidity, and so on and so on. Of course, we have pros and cons for both approaches. If we develop an empirical model, they are more or less easy to be developed. We start from a huge data set and with no specific or expertise on the organism. So with a mathematical or statistical analysis, we can get the formulation of the mathematical model. So we have some positive aspect for empirical models, but on the opposite side, we need a lot of data. So we need to have a wide and representative field data because they are needed for developing the model. It is extremely difficult to make prediction outside the range of input data because the model is not aware of what is outside of the range of data where we were starting from. Something that was how can I say an easy way for producing empirical model is also a big constraint because no information is provided on the biological process. Yes, we don't need an expert for doing this, but no information is provided. And we always need validation and calibration. They are mandatory, that's of course for every type of model. But if we are changing or if we are moving in a different agricultural context compared to the one where we developed the empirical model, there's no we need to validate to see what is the effect, because outside again of the range of the data we started from, those type of model cannot they can fail to work properly. The mechanistic model approach, on the other side, it is based on detailed knowledge on biological process. So we need a multidisciplinary team to work on it. But we can reach accurate and robust data. So we can get simulation of reality that are quite precise, and they are working in very different type of environment. So we can move from one agricultural area to another one without modifying the model. In this way, we can say that those models are highly flexible because we can also obtain some prediction from mechanistic models. We can insert into the model to feed this model with, for instance, weather forecast as an input, and we can obtain some information. Of course, we have some cost and expenses in terms of money, but also in time for developing such a type of model, and we have to validate them. This is true also for mechanistic model, of course. The difference is when the validation is done, a mechanistic model can be used everywhere. Of course, we have to develop some specific experiment or specific research if we have some gaps into the knowledge of the system. Plant models represent a very important and a key opportunity to say, to understand when, if and when we have to apply an intervention in the field. But the point is that this is not enough for practical implementation of IPM. We need to respond to many more and different type of questions. For instance, is the plant susceptible to the infection? Or is the plant already protected by a previous fungicide? And in any case, which type of fungicide should I use for this specific aim of protection? Is the environment suitable for a fungicide application? So we have many different that we should answer before being ready to implement in a very practical way IPM into the field. For this reason, a few years ago, we start to work on the so-called multiple modeling approach. So we stop focusing only on a single disease model, but we try to put together as much model as possible for a specific crop in order to obtain all the information, or the higher number of information, the highest number of information as possible about the different aspects we have to manage for implementing IPM. And actually, we start developing what we call a decision support system. And a decision support system is based on these 4 major steps. Monitoring, so collecting information about the crop and about the environment where the crop is growing. What does it mean? We have to check, we have to collect data about the weather into the field. Yes, of course. We have to observe is the plant is growing properly. So the phenology of the crop. If we have any threat, any weeds, any pest that is affecting our crop. And those data should be collected and analyzed through expert knowledge in such a way to perform alerts, scenario for allowing the decision making taken by the farmer if and how to act. And please note that sometimes the decision is also about what not to do, and not only about what to do. Then we have the action. So the application of proper crop management or crop protection intervention. And they can be of many different types, from agronomical, non-chemical, biocontrol, or chemical intervention. In these 4 stages, we have a decision support system. Of course, these are general principles. They are also useful for describing the decision-making process in agriculture, but a decision support system should be an expert system working with those 4 steps to produce a support, an alert, a scenario, I would say, to give information to the grower, to the farmer, to the agronomist, who is in charge to take the decision, the final decision to implement an action. So we are not talking about a substitution into the decision, but a support tool. And if we go into the field, of course, we have the monitoring step that can be done of very different, where we can use very different tools, from the satellite imaging, from the weather station, from the observation hub for observing severity, incidence severity of a disease, the phenology of the plant. Then all these data should be collected and made available on a repository servers for many different models. We also have the cloud computing power that is today very useful to implement the amount of data we can mm, elaborate and calculate in a short time. Of course, we need proper big data analysis technique for creating prescription app, for creating scenario or alert where the farmer can take decision and move on to the proper to move on to the proper action, so the application of the decision into the field. This action should be the next step for monitoring. So we should have a loop where any action is getting back into the system as a new monitoring information. Of course, we need to mobilize all the decision tools as possible, and they can have a very important impact on IPM. We can integrate decision tools at the very different scale. They are allowing a wider access to the existing technology. We can incorporate IPM solutions, so new techniques, new information and knowledge we can have about new products, new biocontrol agents, new botanical tools, and they can be applied in existing agricultural systems by means of a decision support system. We can support relevant plant health policies, in particular the implementation of the IPM and the principle of the SUD. So we can implement the Sustainable Use Directive criteria for comparing and selecting models to be usefully integrated in the IPM schemes. And how to evaluate the, let's say, quality and how can we trust decision support system. We drafted 5 different eligibility criteria, from the purpose to the approach, the level of transparency of decision support system, if and how it was validated, and the judgment of utility. For instance, the decision support system should be aimed at forecasting a specific characteristic of the epidemic or pest phenology and abundance, particularly those crucial for crop protection. If we are using or if we are creating a decision support tool that is considering an aspect of little significance for the decision making, this decision support system will be of little benefit. The approach, as we already discussed, the different approach is at the very core of the type of model we can use. I'm not saying that one is an old approach and the other one is the correct one. I'm saying that we have to evaluate our needs as farmers, as users of a decision support system, and if we are using just in our area, in the same field, in our farm, a decision support system that has been developed really close to us, most probably we can go for this empirical model. But if we have an empirical model developed on the other side of the world, of the globe, most probably this empirical model will be very hardly fitting to our local conditions. So most probably I have to check for a mechanistic model approach. The level of transparency should be an important eligibility criteria for the selection of the decision support system, because it's often difficult to gain a full access to algorithms of the decision support system tools. Sometimes they are black boxes, so the content is unknown to users. Or if they are partially described, even if published, we can have some detail. Tweaked models with no documentation or of the improvements made remain unknown to users. So look for models that have been published, that are available, and looking on the main, let's say, journals or technical journal, we can have information about them. Validation, as already mentioned, is a very important point. So we need to check for the proper biological validation, so the comparison between the output from the decision support system and the observation in a representative condition. It is a crucial point for epidemiology, for epidemiological model and decision support system. Also, the procedures should be described. It's not only enough to say our model is very good for 95% of the cases. In which condition, under which, in which environment, in how many seasons, and in how many conditions have been tested. So we can check for the type and the quality of the validation. A model, a decision support system that has been validated across the world and very different growing conditions, most probably will be relevant for our scope, also for our scope. Then we have the judgment of utility. So the model is working properly. It is able to simulate the biological phenomenon we are talking about. And we have to check its usefulness into IPM management program. So we should verify if we are gaining an advantage of using such a model in scheduling the action for crop protection. And we also have to evaluate economic and environmental advantages about the use of such decision tool. Thanks a lot, and see you for the next module in IPMWORKS e-learning modules.